Hello, abstract algebra students. We will now begin the proof that matrix multiplication is associative on M2R. This is the longest proof of the section, and it is a little algebraically messy. So here we go. Our claim is matrix multiplication is associative on the set M2R. Now, what we want to show is the definition of associative applied to the set M2R in the operation matrix multiplication. So for all A, B, C in the set M2R, the quantity A times B in parenthesis times C is the quantity A times in parenthesis B times C. Now, we have a for all statement. So we begin by letting A, B, and C be matrices and M2R be given. Now, in order to be able to calculate the products A times B times C in both ways, we are going to actually need to know what these matrices A, B, and C are. So without loss of generality, we may assume that A is the matrix ABCD. B is the matrix EFGH. And C is the matrix IJKL. Now, usually without loss of generality, if you are given matrices, you fill in their entries as letters from the beginning of the alphabet. So we are always allowed, if we are given matrices A, B, and C, to make these assumptions about what the entries are. We could not pick numbers here because that would be losing generality and would be proving by a for all statement by example. But this matrix ABCD is the most general 2x2 matrix for A, and similarly for B and C. So we can make that assumption without losing generality. Now, because we need to prove this equation and both sides look messy, we'll reason both sides into the same matrix. So we'll reason both sides into the same matrix. Consider the following equations. Now, this is just going to be messy, but we will get through it. A times B times C is the expression A, B, C, D times E, F, G, H times, outside of the parenthesis, IJKL. This is just by substitution of what A, B, and C are. See, that's why we needed to assume what A, B, and C were in order so we could plug stuff in. Now, let's do inside the parenthesis first. So if we do out the product inside the parenthesis, we're going to get AE plus BG, CE plus DG, AF plus BH, CF plus DH times the matrix IJKL. If it helps you to cover up a column and work one column at a time and work it out, do that separately. Pause the video and do that if that helps you figure out what the products are. This came by definition of matrix multiplication. Now, let's do the same thing. Let's do the next product out. Let's see, we're going to have AE plus BG times I plus AF plus BH times K. Then we're going to have CE plus DG times I plus CF plus DH times K. That's the first column. In the second column, we're going to have AE plus BGJ plus AF plus BH. See, we had AE plus BGJ plus AF plus BHL. And then we're going to have CE plus DGJ plus CF plus DHL. Again, by definition of matrix multiplication. Now, let's distribute everything. So when we do that, we get AEI plus BGI plus AFK plus BHK. We get AEJ plus BGJ plus AFL plus BHL. We get CEI plus DGI plus CFK plus DHK. And we get CEJ plus DGJ plus CFL plus DHL. Now, the last thing that we want to do is appeal to the fact that ordinary addition is commutative and associative to rearrange the terms in the matrix. And we want to alphabetize the terms in this matrix. And by that, I mean, consider them all as three-letter words, make them appear in alphabetical order. So AEI plus AFK plus BGI plus BHK. then down below here, CEI plus CFK plus DGI plus DHK. The reason we do this is we want to make it easy to compare to the other matrix. When we get the product the other way, we want a matrix that's easy to compare. So this is the first half of the proof. We have worked out A times B in parenthesis times C. Now, in the second half of the proof, we will work out the expression the other way and show that we get the same thing. Stay tuned.